right, guys. Energy level problems. So it's like the Bohr model of the atom. Just sit back, listen. This will be like 5 minutes. So see this energy level diagram? It's like this. Here's the nucleus. You got these energy levels around the nucleus, and that's where the electrons hang out. In general, so let's start with this. We have an electron as close to the nucleus as possible. So what do we refer to that as? That is the ground state. Now, if energy is added to the atom, if energy is added in the form of radiation, so bam, here comes a photon with energy. This electron can get boosted to a higher energy level, right? That's called the excited state. Will the electron stay up there forever and ever? No, it's going to fall back down. When the electron falls back down, what happens? Energy is going to be released by the atom in the form of radiation called a photon. You know, all radiation is made up of these little bundles of energy called photons. Okay, now, on the test, they're not going to give it to you like this. They're not going to show you like the Bohr model of the atom. What they're going to do is they're going to go, boom, here's the first energy level, second energy level, third energy level. It's going to look like this. All right? So on this diagram, the nucleus would be down here. Okay, so what they told us is this: a collection of such atoms with electrons in the n equals 3. Okay, so we have electrons chilling in the n equals 3, the third energy level right here. What they want us to do is they want us to, what, on the diagram above, draw arrows to indicate all possible transitions. So here's what you do. You go, all right, so the electron could fall all the way down, right? All the way down to the first energy level. What else could the electron have done? It could have fallen to there, taken a little break, and then fallen the rest of the way, right? That's the answer to part A. Just show those transitions. Okay, part B. Now hold on. For part B, I want to add something to the diagram. How much energy would this transition here, right here, this first one, from the n equals 3 to the n equals 1, how much energy would this guy be? Well, the ground state is negative 12, and then the n equals 3 is negative 0.75. Hey, notice that energy gets bigger going this way, right? The energy is increasing. What's bigger, negative 12 or negative 0.75? Negative 0.75 is bigger. As you move away from the nucleus, energy increases. Just like when I take this apple right here and move it away from the earth, its energy increases. You know what I'm saying? Okay, so how do we figure out the energy of this transition? Well, what's the difference between 12 and 0.75? 11.25. Okay, electron volts. Electron volts is a unit of energy. Okay, how much energy is this transition? From 0.75 down to negative 3. That's going to be 2.25. Okay, and then this one here is going to be 9. Okay. Calculate the longest wavelength. Now guys, what is longest wavelength in terms of energy? Is longest wavelength going to be highest energy or lowest energy? Well, let's figure it out. Well, here are the equations. The energy of a photon, E equals hf. H is Planck's constant. Don't memorize it. It'll be given. And then the other equation is the wave equation. Velocity is wavelength times frequency because photons travel wave-like. What can we substitute this v with? This v can be substituted with, what type of velocity are we dealing with here? The speed of light. So we put in c right there. So look, c is a constant. So big wavelength, a big wavelength means a what? A low frequency. A low frequency means a what? Low energy. Long wavelength corresponds to low energy. Does that make sense? You sure? Okay. So we're looking, so which transition has the lowest energy of these? The 2.25. Okay, so how do we get the wavelength of that? What you're going to do is you're going to combine these two equations, right? And you get the equation E equals hc over wavelength, right? So take this equation, plug it in for frequency, and you're going to get hc over wavelength. Hc is actually given on this table of constants, h times c. So solve that for wavelength. Wavelength is going to be hc over E. Hc 1,240 nanometer electron volt, and then plug in our smallest energy, 2.25 electron volts. The electron volts cancel, and we get the answer, 551 nanometers. Okay, moving on. Part C. What's the ionization energy of the atom? Well, look, how do you ionize an atom? By pulling electrons off. Or you could add electrons if you're making the atom negative. But look, so the ionization energy would be like if you have an electron here in the ground state, if you take that electron and pull it off the atom, what did you do to the atom? You turned the atom into a positive ion. When an atom loses an electron, it becomes positive. How much energy is required to pull this electron off the atom? Well, see right here, this is infinity. Infinity refers to like it's off the atom. So how much energy is required to yank that electron off? 12 electron volts, right? From here to there would be 12 electron volts. That's the answer. Easy. Okay, D, photons of energy, 11 electron volts. Let me just revert this, clean this up. Oops. Nope, don't want to do that. Okay, so we got an electron here. So we have a photon coming in. Energy comes in. Bam. This is 11 electron volts. Now, where would that boost this electron to? Let's see, 11 electron volts. This is at negative 12. This would need to be where? We would need to have an energy level at what? Negative 1. Is there an energy level right here at negative 1? No. So is there like a platform for this electron to land on? No, there's no platform. So the answer is nothing happens. Nothing happens. Because there's no, there's no energy level at negative 1 there. Does that make sense? Could it land on here? It would kind of like shoot past there, I'll be honest with you. I had the exact same thought that you just had. But for that to occur, what they would need to say is photons of energy, like 0 electron volts to 11. Like they're like a range. But if it were 11 electron volts, because how much energy is needed to go here? 9. So it's going to go past that, and it would need to land somewhere in here. But there's no landing platform there. Okay, last one. Photons of energy, 14 electron volts, hit the atom. What will this do to the atom starting if the electrons start down here and the n equals 1? 14 electron volts, what's it going to do? How much energy is needed to pull it off the atom? 12, and we have 14, so what's going to happen to this electron? It's coming off the atom. The answer here is it will ionize the atom. The atom will become an ion.